We're going to look in this lesson at how we can use what we've learned about distance, midpoint gradient, parallel and perpendicular lines when it comes to solving problems related to quadrilaterals, and particularly we're going to look at how we can use those different concepts to prove that a quadrilateral is a particular quadrilateral. So for example, right, so we're going to look at 4 examples. You're given 4 points, H, E, A, and R, and their coordinates are described as well. And you're told that the vertices of a quadrilateral HEAR, right, drawn for you as well. Prove that quadrilateral HEAR is a parallelogram. And so, you know, we know the properties of parallelograms. We know that a parallelogram has opposite sides parallel. It also has opposite sides equal. We know that their opposite angles are equal. We know that their diagonals bisect each other. So if we're looking to prove that a shape is a parallelogram, then it is sufficient to prove any one of those things. And you know, that's actually a very complex statement to make, so I'm just going to delve into it very quickly. But when you decide how to prove that something is a parallelogram, how you need to reason with yourself is that one condition enough to make the other properties necessarily true as well? And what I mean by that is, for example, if all I do is show that my opposite sides are equal, is it necessarily true that the opposite sides are also parallel just based on that? Is it also necessarily true that my opposite angles are equal? Is it necessarily true that my diagonals will bisect each other? And I'm going to show that yes, just based on opposite sides being equal, all the other properties will also hold. So first off, I'm going to show that my opposite angles are equal. If I'm to draw in this diagonal, right, then I create 2 triangles. And these 2 triangles are congruent using the side, side, side reason, right? They have this side equal, and this side is common. So they're congruent, they're identical triangles, which means that their angles are also going to be identical. And more specifically, the angle between these 2 sides will be the same as the angle between these 2 sides. And you can use a similar process of reasoning to argue that this angle, will be equal to that angle. So if you're to draw in this diagonal instead, then you'd also have 2 congruent triangles, and therefore those 2 angles are equal. So I've managed to show that opposite angles are equal. Now I'm going to show that the opposite sides are parallel, right? And so what we have is, if I call this angle x and I call that angle x, right? So, I mean, if this angle is x, then this angle is also x, because I've shown that those 2 angles are equal. So the angle sum of these angles is going to be 360, because angles in a quadrilateral add up to 360. So I'm going to have x plus star is equal to 360. And so 2x plus 2 star is equal to 360. And so basically x plus star is equal to 180, right? And so that means that the co-interior angles add up to 180, which means that these lines must be parallel, right? If x and star add up to 180, then the co-interior angles are supplementary, which means that the lines are parallel. And the same would be true of these 2 lines, because x and star, the co-interior angles there, are supplementary. So now I've shown that my 2 sets of sides are parallel. And then finally, we want to show that our diagonals bisect each other, right? So we want to show that this side is equal to this side, and that this side is equal to this side. And again, we use the idea of congruent triangles. So since we've shown that the opposite sides are parallel, we know that this angle will be equal to this angle because of alternate angles, and that angle will be equal to that angle also because of alternate angles. And so we have angle, angle, side, right? We have the same set of angles here and an equal side, which means that these two triangles must be congruent, they must be identical, right? And so the side that's next to this angle, right, this side is equal to this side, and this side will be equal to this side, and likewise this side will be equal to that side. Okay, I've already used two stripes. So what I'm demonstrating is that just based on my opposite sides being equal, I've shown that all the other properties necessarily hold. Or likewise, if I were to show that, just to show that my opposite sides are parallel, right? If I were to prove that opposite sides are parallel, does that make all the other things about a parallelogram true in this shape? And the answer is yes. So we know that these two would be dot and 180 minus dot, and this would also be dot because of co-interior angles, right? And these two would also add up to 180, so this would also be 180 minus dot. So already I've shown that my opposite angles are in fact equal. I want to show that my opposite sides are equal, so I'm going to draw in my diagonals, and we can see that this angle is equal to this angle because of alternate angles. These two are equal because of alternate angles. Okay, wait, scrap that idea. Okay, so if I want to show that opposite sides are equal, how I can go about doing that is I can just introduce one diagonal, right? And I've created congruent triangles because we know that this angle is equal to this angle, and that angle will be equal to that angle, right, using alternate angles. And because we've got angle, angle, side, right, this side is common to both triangles, then that would mean that this side is equal to this side, and this side is equal to that side, right? So this is just an example of how, you know, based on whatever property you choose to demonstrate that a particular shape is a rhombus or a parallelogram, you need to make sure that what you've chosen to prove is sufficient to prove that that shape is, without a doubt, whatever you're saying that it is. And we'll see an example at the end where, you know, you have to be particularly careful about that. Right, so to prove that HEAR is a parallelogram, we can show that opposite sides are parallel. So we could work out the gradient. We could work out the gradient of AE, the gradient of RH, see if those are equal, the gradient of AR, gradient of EH, see if those are equal. So maybe let's do that just for the sake of completion. So the gradient of AE will be 7 minus 2 over minus 3 minus minus 1, which is 5 over minus 2. The gradient of RH will be 5 minus 0 over 2 minus 4, which is 5 over minus 2. And the gradient of AR, right, so this guy over here, will be 5 minus 7 over 2 minus minus 3. So that would be minus 2 over 5. And the gradient of EH will be 0 minus 2 over 4 minus minus 1, which will be minus 2 over 5. Right? And so because the gradient of AE is equal to the gradient of RH, that means that these guys are parallel. Right? So AE is parallel to RH. And the gradient of AR is equal to the gradient of EH. Right? And so that means that AR and EH are also parallel. And therefore HEAR is a parallelogram. Alright, so that was quite a calculation heavy way to go about proving that HEAR is a parallelogram. A shorter way that we could have gone about that is, so let's just take a bit of a detour. Right, so one of the things that we know about a parallelogram is that its diagonals bisect each other. But is that enough? So is that property enough to prove that a shape is a parallelogram? So if I were just to show that the diagonals bisect each other, would that be enough to say that that shape is definitely a parallelogram? So let's say that we know that this is equal to this and this is equal to this. Based on this, am I able to prove every other property of a parallelogram? And the answer is yes, right? So first I'm going to show that the opposite sides are equal. So if I call this angle dot, then the opposite angle is also dot. And so using the side angle side reason, we know that this side is going to be equal to this side, right? These triangles are congruent, and therefore those two sides would be equal. And you can use a similar reason for the other sides, right? If this angle is hard, then the vertically opposite angle will also be hard. So then you have an identical side, an identical included angle, and another identical side, right? Which tells me that these two triangles are congruent, and so this side will be equal to this side. And we've already seen how if the opposite sides are equal, then all the other properties hold. So I'm not going to go into that proof again. But what I wanted to show is just based on knowing that the diagonals bisect each other, that is enough to prove that my shape is a parallelogram. So how can I determine whether the diagonals of HEAR bisect each other? Well, if they bisect each other, then we'd know that this side is equal to this side, and this side is equal to this side. More specifically, we would know that the midpoint of ER is the same as the midpoint of AH, right? The middle of AH would coincide with the middle of ER. So let's work out the coordinates of M, right? So, well, okay, let's not be presumptuous. So let's say then, let's work out the coordinates of the midpoint between E and R. So that would be -1 plus 2 divided by 2. And the y coordinate would be 2 plus 5 divided by 2. And so that would be minus, no, not minus. It would be positive 1 over 2. And y coordinate would be 7 over 2. So that's the midpoint between E and R. Let's work out the midpoint between A and H. So that would be -3 plus 4 divided by 2, and 7 plus 0 divided by 2. And so the midpoint of AH would be positive 1 over 2, 7 over 2. And because the midpoint of ER is the same as the midpoint of AH, that would mean that AH and ER bisect each other, right? They halve each other. And so therefore, HEAR must be a parallelogram. Okay, right? Then you're asked to prove that HEAR is a rhombus. Okay, and there's a lot of things that you know about a rhombus. First of all, it has all the properties of a parallelogram, right? So proving any property that belongs to a parallelogram is not going to be enough to prove that this is a rhombus, right? So proving that the opposite sides are parallel is not going to prove that this is a rhombus. We need to think about what makes a rhombus, right? What makes it a special parallelogram, basically. And there's a couple of things. There's the fact that all its sides are equal, right? So that's the one distinguishing thing. the other thing, so if we think about its diagonals, we know that its diagonals meet at 90. That's very important. Another important thing is, well, the diagonals bisect each other, but we know that that belongs to parallelograms in general, so that wouldn't be enough to prove that it's a rhombus. We know that the diagonals bisect the interior angles, but at this stage of our study of analytical geometry, we are not really involved with angles beyond 90 degrees, so 90 degrees is the only angle we really work with at this point in analytical geometry. So we're not going to use information about angles to prove that this is a rhombus, is what I'm saying. So, you could, I guess, do some trigonometry and figure out what that angle is and figure out what that angle is, right? So if you figured out what this distance is and you figured out what this distance is, so you would be able to figure out what that is and show that, if this angle is equal to this angle, then it must be a rhombus. And that would be very interesting. But yeah, we're not about to complicate our lives like that. So what we're rather going to show is, you could go the equal sides route, right? If you show that all the sides are equal, then you'd show that it's a rhombus. But that's a lot of work, because then you'd have to work out what AE is, what AR is, what RH is, what EH is, and show that they're all equal. I think the easier thing to show here is that the diagonals meet at 90. And this is the important thing about how you need to know the properties of quadrilaterals very well. Because if all you know about a rhombus is that their sides are equal, then you're going to be stuck doing things the long way, which isn't wrong, it's just not efficient. Whereas if you know that the diagonals meet at 90 degrees, then all you need to show is that the gradient of AH times the gradient of ER is equal to -1, right? If they're perpendicular, then we know that that relationship must be true about their gradients. So let's work out those gradients. So the gradient of diagonal AH will be 7 minus 0 over minus 3 minus 4, which is 7 over minus 7, which is -1. And the gradient of ER is equal to 5 minus 2 over 2 minus -1, which is 3 over 3, which is 1. And indeed, the gradient of AH times the gradient of ER is equal to -1. And so AH is perpendicular to ER, right? Which would mean that HEAR is a rhombus. Right, and just to demonstrate again, this is the last I'll do of it, the fact that just showing that the diagonals of a shape meet at 90 degrees necessarily means that it's a rhombus, right? So all I know about this shape is that it's four-sided and its diagonals meet at 90 degrees, and the challenge is to show that every other property of a rhombus is also true about this shape. So, okay, so actually, as it turns out, it's wrong, right? It's not sufficient to just show that the diagonals meet at 90, because for all we know, this could be a kite, right? The diagonals meeting at 90 degrees does not necessarily show that it's a rhombus. But based on the fact that it's a parallelogram, so we've already shown that it's a parallelogram, which means that we know that the sides are parallel. We know that the opposite angles are equal, right? We know that opposite sides are equal. So essentially what we're trying to show is, if a shape is a parallelogram and its diagonals meet at 90, is that sufficient to show that it's a rhombus? So what we need to show, the outstanding properties that we need to show, are that the sides are actually all equal, so it's not just opposite sides that are equal, right? And the diagonals bisect the interior angles, right? So since it's a parallelogram, the other thing we already know is that this side is equal to this side, and this side is equal to this side. So these are the two things we still need to prove in order to demonstrate that this is, that just knowing that these meet at 90 degrees proves that these are also true, right? So we can start by saying that, well, all these angles are 90, right? Because these diagonals are perpendicular. And so because this side is equal to this side, and this side is equal to this side, and because it's a parallelogram, we know that this side is equal to this side. So these are congruent triangles, right? So this triangle and this triangle are identical, but then they must also be identical to these triangles, because these triangles also have this side, that side, and an included angle of 90. So these sides are actually all equal, right? And as for whether the diagonals bisect the angles, so that all comes down again to the idea that the four little triangles are all identical, so their angles are also going to be, they're going to have the same set of angles. So if you kind of do this in a less messy manner, you'll see that this angle is equal to this angle, and this angle is equal to that angle, and using alternate angles, this angle would also be dot, this one would also be dot, etc. So this is all to say that just showing that the diagonals meet at 90 degrees is sufficient. After I've proven that it's a parallelogram, it is sufficient to say that because the diagonals meet at 90, then this shape must be a rhombus. It's a special parallelogram. Right, okay, I'm going to speed through the rest of the examples, so I'm not going to go to painstaking detail. If you're unsure, whether a property that I've chosen to prove is sufficient to prove that, a particular shape is whatever we're trying to prove it is, then I encourage you to pause the video and kind of reason about it, to say, well, okay, if I just had this one property for my quadrilateral, would I be able to prove everything else? Would I be able to prove all the other properties of the quadrilateral that I'm claiming it is? Cool. So you're given quadrilateral LAND, and you're asked to prove that it's a parallelogram. So again, I'm going to go the diagonals route. So I'm going to show that the midpoint of LN is the same as the midpoint of AD, right? Because then I will have shown that the diagonals bisect each other, and therefore it's a parallelogram. So the midpoint of LN is going to be -5 plus 6 over 2 and 3 plus 6 over 2. So the midpoint of LN will be 1/2 and 9 over 2. And then the midpoint of AD will be -3 plus 4 over 2 and 0 plus 9 over 2. And that would be 1/2 and 9 over 2. And because the midpoint of LN is the same as the midpoint of AD, that means that LN and AD bisect each other, and so then LA and D is a parallelogram. Okay, then you're asked to prove that LA and D is a rectangle. So now we need to think about what makes a rectangle even more special than just an ordinary parallelogram. A couple of things. The diagonals are equal, and we also know that all its angles are 90 degrees. And of course, then if we know that it's at least a parallelogram, we know that opposite sides are parallel, right? So if I can show that one of the angles is 90 degrees, just one of them, then it will be necessarily true that the others are also 90. So what I mean is, I don't need to show that this is 90 and this is 90 and this is 90 and this is 90, Because I've proven this is a parallelogram, then I know that these sides are parallel. And so if this angle is 90, this angle will be 90 because co-interior angles. This angle will also be 90 and that angle will also be 90. So all I need to do, and I think that's the easiest thing to do in this case, is to show that any of the angles is 90. So I'm going to say, show that angle A is equal to 90 degrees. And basically what that means is I need to show that the gradient of AL times the gradient of AN is equal to -1. I need to show that my two lines are perpendicular. And I think it's useful to start out a proof by kind of setting that out for yourself. You know, what are you aiming to prove? So I'm going to find the gradient of AL, which is 9 minus 3 over 4 minus 5, which is 6 over 9, which is 2/3. The gradient of AN will be 9 minus 6 over 4 minus 6, which is equal to 3 over -2, right? Okay, something strange has happened. Right, so that would be equal to -3 over 2. And so 2 over 3 times -3 over 2 is indeed equal to -1. Therefore, we now know that AL is perpendicular to AN, right? Or in other words, A is equal to 90 degrees, right? And therefore, LAND is a rectangle. Okay, right, you're given 4 points. LMNP are the vertices of a parallelogram LMNP. Well, that actually is very tricky to say. Determine the coordinates of N. So, useful to draw a sketch. L is -1, -1. M is -2 and 4. N we don't know. P is 4 and 0. Okay, and the important thing is that the naming convention of a shape is that the vertices, you name the vertices in order, alphabetical order. So it's going to be L, M, and then N would have to be somewhere this side in order for this to be a parallelogram, right? And join with P and then go back there. So what I mean by that is you wouldn't have something like LP, then go to M and then go to an N, right? So even though that would create a parallelogram as well, that would mean that your shape is not being named in alphabetical order. So that wouldn't be a possibility. So L, M, and then N must be somewhere in here, P. So we're trying to figure out the coordinates of N, right? So you could go the distances route, right? If you know that a shape is a parallelogram, then you know opposite sides are equal. So you could say, well, okay, let's figure out an expression for Mn, and we know that that must be equal to this distance. But because you're trying to work out x and y, you're going to need a second equation. So you'd have to figure out an expression for this distance as well, and equate it to this distance, and then solve simultaneously, which could be heartache. Another way you could go about it is you could say, well, again, you could use the idea of parallel lines. So the gradient of this line is going to be equal to the gradient of this line. But because you have two unknowns, you'd also have to make an equation with these two gradients. So this is equal to this, and then solve simultaneously, which is also painful. I think that the best bet is to use the idea that the diagonals bisect each other. So the midpoint of this diagonal is going to be the same as the midpoint of that diagonal, right? So the midpoint of Ln is equal to the midpoint of MP. And the midpoint of MP is -2 plus 4 over 0, over 0, over 2, and 4 plus 0 over 2. And so that midpoint is 2 over 2, which is 1, and 4 over 2, which is 2. So we now know that the coordinates of that midpoint are 1 and 2. Right? And so the midpoint of Ln is minus 1 plus x over 2. And the midpoint of the y coordinate will be minus 1 plus y over 2. And we know that that's equal to 1 to 2. So effectively that gives you two equations to work with, right? So we know that the y coordinate, which is minus 1 plus x over 2, is going to be equal to 1. And you can solve that by inspection. Something divided by 2 is 1. That must mean that minus 1 plus x is equal to 2, right? 2 divided by 2 gives me 1. And so x would be equal to 3. And then the second equation is my y coordinates. So minus 1 plus y over 2 needs to give me 2, right? What do I divide by 2 to get 2? That something must be 4. So minus 1 plus y must be equal to 4. So y would be equal to 4 plus 1, which is 5. So the coordinates of n would be 2. No, not 2. X is equal to 3 and y is equal to 5. Right? Show that MP is perpendicular to Ln and state what type of quadrilateral LMNP is other than a parallelogram. So we want to show that this angle here is 90, and we already know that if that is true, then this is a rhombus. Right? We can't get more specific than that because then we'd need to know that the interior angles are 90 degrees, and we don't have enough information to prove that as yet. So I mean, just based on the diagonals meeting at 90 degrees, that's not enough to say that the interior angles are 90 and therefore this is a rectangle or this is a square or whatever. So the most we can say is it's a rhombus. So in order to show that they meet at 90, I'm going to work out the gradient of Ln, which is 5 minus minus 1 over 3 minus minus 1. So that would be 6 over 4, which is 3 over 2. Then I'm going to work out the gradient of MP, which is 4 minus 0 over minus 2 minus 4. So that would be 4 over minus 6, which is negative 2/3. And if you work that out, MLN times MMP is equal to minus 1, right? 3 over 2 times negative 2/3 is minus 1. And therefore, Ln is perpendicular to Mn, right? So we've proven what we needed to prove. And so we now know that LMNP is a rhombus, right? And then you're asked to show that oh my God, why is it so hard to say L? LMNP is a square. So it wouldn't be enough to just show that this is 90. I mean, okay, so there's a couple of things we know up front. We know that because it's a rhombus, these sides are parallel. We know that these sides are equal. And all sorts of cool things. So in order to show that this is specifically a square, we would have to show that this is a 90-degree angle, because then that would mean that these other angles are also 90 because of the parallel lines. So if we can show that one of the interior angles is 90, then we've done a home run. We've shown that this is a square. So in order to do that, again, I'm going to use gradients. So I'm going to work out the gradient of the line ML, which is 4 minus minus 1 over minus 2 minus minus 1, which would be 5 over minus 1, which is negative 5. And then the gradient of LP, is 0 minus minus 1 over 4 minus minus 1. So that would be positive 1 over positive 5, right? And you'll see that they are negated reciprocals of each other. ML, the gradient of ML times the gradient of LP is indeed equal to negative 1. Therefore, ML is perpendicular to LP, or you can say that L is equal to 90 degrees, and therefore LM in P is a square. Okay, then you're given 4 points. You're going to plot them. And they're all in the first quadrant, so I'm just going to do that. So A is equal to 2 and 7. B is 6 and 7, so same horizontal. C is 8 and 1. And D is 3 and 4, so maybe somewhere. Okay, and you're asked whether A, B, C, D is a kite, right? So you could decide to work out this length and see if they're equal, and this length and this length, and see if those are equal, right? And maybe as an exercise, think about whether that would be sufficient to show that it's a kite. Well, the answer is yes, it is sufficient, but think about why it's sufficient to show that it's a kite. But say instead I decided that I just want to show that my diagonals meet at 90, and that will show that it's a kite. So the gradient of AC would be 7 minus 1 over 8 minus 2, which is 6 over 6, which is 1. And the gradient of BD would be 7 minus 4 over 6 minus 3, right? Which is what? Wait. Okay, wait, there's a fish in something I've done. Oh, okay. So over here, I made a boo-boo. All right. So I started with A, but then in the bottom I started with C. So this would be 2 minus 8 instead. This would be minus 6, and the gradient would be negative 1. Okay, and then back to BD. This would be 3 over 3, which is positive 1. So AC is perpendicular to BD, right? The product of my gradients is negative 1, which means that AC is perpendicular to BD. But have I proven that this is a kite? Do all the other properties of a kite hold just by me showing that these two lines are perpendicular? And the answer is no, right? So if you were to imagine something like this, where two lines are diagonal, perpendicular, right? And you join their endpoints with straight lines, not with these curvy things that I've drawn, it's very clear that this is not a kite, right? So my diagonals just meeting at 90 degrees is not enough to show that the shape is a kite. I'd need to prove something else over and above that. So for example, if I prove that they're diagonal and this diagonal is bisected by the other diagonal, right? So then I'd have a situation like this, where this side is equal to this side, and these guys meet at 90. And this shape would be a kite, right? Because since this is a common side to both these little right angle triangles, then we've got side angle side, which shows me that this side will be equal to this side. And by a similar reason, so if you look at these, so if you recognize that that's 90, this triangle and that triangle are also going to be congruent by side angle side. So that would mean that this side is equal to this side as well. And from there, all the other properties hold as well. So this larger triangle and this triangle are also congruent using side, 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 right? All their sides are the same. So that would mean that this angle is equal to this angle. And also using the fact that these two triangles are congruent, we'd know that this angle is equal to this angle is equal to this angle. So basically that's just about the symmetry that's happening over this line, right? If I fold this side over to the other side, then they're identical. So anyway, this is all to say, just showing that they're perpendicular is not enough to show that it's a kite. But if you show that they're perpendicular and that the one diagonal bisects the other, then that proves it's a kite. So over and above showing that they're diagonal, I also need to show that this point over here is the midpoint of BD. So how we could go about doing that, this is a bit advanced, is we could say, well, the midpoint of BD is 6 plus 3 over 2 and 7 plus 4 over 2, which is 9 over 2, and the y coordinate is 11 over 2, right? So basically what we want to show is that this, the line that goes through A and BD, well, let's rephrase that. A, M, and C are all connected by one straight line. That's what we want to show, right? And so in order to show that, one way we could go about that is we could show that the gradient of this line is the same as the gradient of this line. That's the only way that they can all lie on one line, right? If the gradient from here to here was different to this gradient, then there'd be a little conk, right, from M to C. And so the fact that they're on one line must mean that the gradient of the line from A to M must be the same as the gradient from M to C. So let's work that out. The gradient from A to M would be 11 over 2 minus 7 over 9 over 2 minus 2. So that's 5.5 minus 7. That's minus 5 over 2. Is that right? That is not right. Yes, okay, it's supposed to be minus 1.5, sorry. That would be minus 3 over 2. And 9 over 2 minus 2 would be 5 over 2. And so that ends up being negative 3 over 5. And then the gradient of MC, so the line from M to C, would be 11 over 2 minus 1 over 9 over 2 minus 8. And that would be 9 over 2 over 9 over 2 minus 8, which is minus 7 over 2. And that's negative 9 over 7. And because these aren't equal, right, so the gradient from A to M is not equal to the gradient from M to C. That would mean that A, M, and C do not lie on the same line. Okay, and what does that mean to us? That means that, you know, M is not on this diagonal, right? M is not on this diagonal. It's somewhere maybe over there, who knows, right? So AC is not bisecting BD, right? So AC does not bisect BD. And therefore, as much as they meet at 90 degrees, Because the one diagonal isn't bisecting the other, that must mean then this is not a kite. And I mean, I guess the responsible thing to do would be to check that, you know, is maybe this diagonal bisecting this, right? So that would be another thing to check before you conclude that it's not a kite. But yeah, I leave that to you as an exercise, I guess. So figure out the midpoint of AC and reason about whether that midpoint is on this diagonal or not. But you will see that it isn't on the diagonal, and therefore ABCD isn't a kite. Right? So maybe in this case, what would have been easier to prove whether it's a kite or not would have been to work out the lengths, right? So work out how long this is, work out how long this is, work out how long that is, and finally work out how long that is, right? Because actually, if we're to go this route, so if we showed that, you know, the two lines are perpendicular, but the one diagonal doesn't bisect the other, for the sake of completeness, you'd have to show that AC is not bisecting BD and BD is not bisecting AC. So that would be a more cumbersome proof. So I would say in this case, the more fail-proof way to prove that it's not a kite would be to say, to show that the adjacent sides, one of the pairs of adjacent sides is not equal. Right? And now you're asked to prove, well, not to prove, to move point D so that you do have a kite. So I'm just going to redraw this quick. So I've just drawn in that the 1/2 of the kite. And the important thing to remember about a kite is that it has symmetry, right? So you would want to basically replicate the side you already have on the other side of the red line. So you would want to go down however many units. So this is 4 units long, right? To go from here to here is 4 units. So you'd want to go down 4 units, and that would give you your coordinates for D. Right, so that's 4 units down from 2, 7, so that would be 2 and 3. Right, and then you could connect these two. Okay, or another way that you could have thought about it is, you know, maybe you might have thought about it as I need to replicate this side over here as well, right? And so how you could do that is you could say, well, how many units am I climbing to go from C to B? I'm climbing 6 units, and then I'm running backwards for 2 units, right? So if I had to replicate that in the mirror, instead of rising 6 units, I would run 6 units, right? So that would take me back to an x coordinate of 2, right? So from 8, 6 units backwards would be 2, and then I would rise 2 units. So that would be 2 units over there. And if I'm rising from 1, that's going to take me to, okay, so this is a terribly scaled diagram, but let us just forgive. Right, so that would be 2 units. And so the coordinates of this point would have to be 2 and 1 plus 2, which is 3, which is what we got before. So that way, this line would be a mirror for the line that we highlighted before. So either way that you do it, those would be the coordinates for D. Another way that you could think about it, okay, wait, no, I thought about it, and this lesson's already very long, so let's just leave it at that.